Hola amigos, so let's continue with power available with maximum velocity for reciprocating and jet engine, and also we will observe altitude effects on power required and power available. So from page number 410 to 414 we will be doing all this. Okay, so let's start, and just before that please write down these unit conversion and standard values. I have added this 1 horsepower is equal to 746 watts, which was not added earlier in this, and these units and standard values are used in every flight mechanics and stability and control, aerodynamics, propulsion, and please write them down. So let's continue with power available and maximum velocity. So for a piston engine and jet engine, they both show different power available variation for different velocities. Okay, for given range of velocity, the power available variation for piston engine and jet engine will be different. For the same airplane, we have same amount of power required to overcome drag for a given range of velocity, but power available depends upon the type of engine. And that's why we have different power available variation for given range of velocities. And in a piston engine, we have the power which is transmitted from piston to the crankshaft, and through crankshaft it is transmitted to this propeller, and depending upon the efficiency of propeller, it makes the power available to the aircraft. And the power generated by the reciprocating engine is known as brake horsepower, shaft brake horsepower, because this power that is generated in the engine is transmitted through the shaft to the propeller, and depending upon the efficiency of the propeller, the power will be available for the aircraft to fly. Okay, so power available for an aircraft will be equal to the efficiency of the propeller multiplied by the power that is generated in this engine, which is the shaft brake horsepower, and it is also expressed in terms of horsepower available, which is equal to efficiency of propeller multiplied by the brake horsepower. Okay, in terms of horsepower, it is horsepower available equal to efficiency of propeller multiplied by brake horsepower. So power available variation is like this, it varies like this, which is we can say very crudely we can say it is nearly a constant. Like the thrust required variation for jet engine was nearly constant for a given range of velocities, and here the power available is equal to the thrust available multiplied by the velocity. So y equals to mx is this graph, y equals mx, where thrust available will be the slope, and it is a linear variation, whereas it is a constant. We are saying it in crude terms, it is quite constant, and these are typical curves for a piston engine and a jet engine. And for power required, we have earlier seen that power required for an aircraft depends only on the layout or the design of the airplane, not on the type of engine, which is why if we have a set of jet engine or a piston engine on the same airplane, we will have the same power required variation for a given range of velocity. So power required is this, and we have just superimposed this power available for piston engine in this green dots and power available for jet engine in this red dots. And when they both intersect at high velocities, velocity is increasing in this direction. At high velocities, when the power required is intersecting with the power available at high velocity, it will give us the maximum velocity with which an aircraft can fly. And this maximum velocity for this linear curve intersection with the power required is the maximum velocity which a jet aircraft can attain. And for a propeller engine, it's nearly constant, as I said here. So its intersection at high velocities, power available intersection at high velocities with power required at that high velocity will give us the velocity which is maximum for a propeller engine. Okay, so now moving on to the effect of altitude. Okay, when the aircraft is moving from sea level to a height, how does the aircraft perform, or how does the power required or power available to the aircraft varies? Okay, we will see through these graphs how will they vary, and from these formulas we can verify that here which we will be seeing are correct. Like we know that velocity is equal to 2w by rho scl with under root, and we have derived this from lift equals to weight, and velocity at sea level is given by this formula with density at sea level, which is rho naught. We can also represent this as v naught. Okay, so rho naught is here is the density at sea level. We are seeing all these formulas, or say variation, keeping cl and cd of an aircraft fixed. Okay, we have to keep some parameters fixed in order to see the variation of other parameters with respect to other parameters like power required and velocity variation. We have to see with respect to altitude, which is governed by density variation. So these variation will be observed by keeping the cl and cd of an aircraft fixed. Basically cl is kept fixed, and cd of an aircraft is the result which becomes fixed because cl is fixed, because cd is equal to cd naught plus cdi. We know from drag polar equation, cd is equal to cd naught plus cdi. cd naught does not depend upon cl, so it will be constant, and cdi is equal to kcl square. Cl is constant, so cd will be overall constant, which is cd naught plus cdi will be constant. So now we see that velocity at sea level is given by this. Power required is equal to thrust required into velocity. Okay, so thrust required into velocity will give us this formula for power required. At sea level, we will substitute the density with rho naught, and it is 2w cube cd square divided by rho naught s cl cube whole under root. And if we want to observe the velocity and power required at a height, keeping cl and cd same, Okay, they both are not equal to each other, that is CL and CD are not equal to each other, but CL is constant and CD is constant. Okay, so only the density is changing. These all we are observing for an aircraft while performing in a steady and level flight. Okay, so velocity at a height will only vary when the altitude varies, and when the altitude varies, with altitude we know density varies. So density at sea level we know is high. As we go above the earth's surface, the density level decreases. So density decreases, velocity should increase. Okay, so velocity will increase and pressure required will also increase. So let's see, if we say that minimum velocity which is at sea level is the stall velocity with which an aircraft must fly. It should not fly actually, because at stall velocities the aircraft may experience a drastic reduction in lift, because when it reaches CL max it may experience a sudden gust or sudden wind which may further increase the angle of attack of the airplane. So it should fly above the stall velocity. So actually stall velocity is the minimum velocity with which an aircraft can fly at sea level. Okay, so and if we see this graph, let's say we know this is the variation of power required, and not power required at sea level is also represented by PR with a knot over here, and similarly we can say velocity at sea level is given by V with a knot over here. So power required is at sea level is PR naught, whose variation is this. So if we say minimum power required is over here and minimum velocity is vertically tangent to this power required curve, it is this. So V stall will be this velocity at sea level. Okay, and at stalling velocity CL will be maximum, but here we are keeping CL fixed and CD also fixed. Okay, and as the altitude increases, the density decreases. Okay, and velocity increases and power required increases, because the air gets thin and the power required to fly that aircraft with the same thrust equal to drag will increase. Okay, so when aircraft will be flying at thrust equal to drag at sea level, the density is rho naught, which is high, and when it reaches at a height and it experiences low density but thrust is required to be maintained equal to drag, for that power required will be increasing. So we can find that power required increase will be these points for different velocities, and when joined it will give this same variation like this power required at sea level, but as at the sea level the variation is this, which we know earlier, we did this here also. But as height is attained by the aircraft, the power required curve shifts a little upward, because power required is increasing as it attains the height, and with that we saw that it is not only moving upward but also moving rightwards, and also it is tilting a little clockwise. If you see carefully, it is tilting a little clockwise. Okay, so at sea level it is this, and if the aircraft fly at a height h1, the power required for different range of velocities will be this red line, and at further higher altitude the power required will further increase and the curve will move further up and towards right. Okay, and it will also rotate a little in the clockwise direction. So how the variation is actually taking place can be seen from this formula, like V at sea level, velocity at sea level is calculated from this. We just need to multiply by the density ratios and their under root. On dividing this we got this formula, and upon dividing this we got this formula. So the velocity at a height is this, let's say. So the power required at a height will be corresponding to this. At this velocity is at velocity at a height, and the power required corresponding to this will be here with respect to that height. And now we will see the maximum velocity here which the jet aircraft and propeller aircraft have attained here. Their variation with respect to altitude we will be seeing here. Okay, so as we can see, power required at sea level is this biggest bold black curve. Okay, we know. Now from here we know as the aircraft moves above the sea level, the power required increases, or say the curve moves up and towards right also moves clockwise. So this power required curve, this black curve is drawn dotted over here, which is moved upward and towards right and rotated clockwise. Okay, so this power required curve at a height is like this. Okay, now comes the power available. So the power available varies, like for piston engine the power available is this in the green. Okay, power available at sea level, which is power available for propeller at sea level, PA P0, which intersects with this power required at sea level at this point. So this is the maximum velocity with which aircraft can fly with propeller engine at sea level, and corresponding power available and power required at sea level will be same. Okay, at this point. And for the jet engine the power available curve is this, y equals mx. So when it is plotted, power available for jet engine PA J0 at sea level, power available for jet engine at sea level, it intersects at a point ahead of this intersection of power available of propeller engine at sea level. So its intersection is quite ahead of this propeller plane, and this shows that velocity corresponding to this intersection is quite high with respect to this velocity of this propeller engine. So maximum velocity, actually we are seeing maximum velocity is the intersection of this power available of jet engine at sea level and intersection of power available at that high velocity with the power required at sea level at that high velocity, gives us the velocity which is maximum at sea level. So from here we got sea level maximum velocities for jet engine and propeller engine, and with increasing height density decreases, and we will see that power available curve is going down for this propeller engine. This green one is power available for propeller engine at sea level, and when the aircraft moves from sea level to a height, the power available curve moves down. Okay, so also the power available for jet engine, which is y equals mx curve, for sea level also moves down or gets little downward slope. Okay, which is given by this dashed red line. Okay, so the intersection of this power available for this propeller engine at a height with power required at a height, this dotted line in black and this green dotted line, will give us the maximum velocity with which the aircraft can fly at a height. Okay, so similarly we can see that this is the power available for jet engine at a height, and power required for power required is the same for both jet engine and this propeller engine, and the intersection here will give us the maximum velocity for the jet engine. Okay, the red and black intersection over here will give us the maximum velocity. And please note that if we talk about the minimum velocity with which an aircraft can fly at sea level, is the velocity of stall velocity. Actually, stall velocity is the velocity with which an aircraft can fly at sea level. Minimum velocity it is, and it is given by this tangent when drawn vertically over this power required curve at sea level. And we cannot do the same thing for minimum velocity calculation for power required at height curve. Okay, we know power required at height is given by this black line, and V stall is this. Okay, so V stall is this, but the minimum velocity, if we see from the intersection of power available, actually power available for a propeller plane at a height intersects the power required curve at a velocity higher than this stalling velocity, so it cannot fly with a velocity less than this minimum velocity. Okay, so that's all for now. Thank you.